decades, I would say. And like, well, all kinds of things. But more recently, he's been working and doing very interesting work in well, characterizing quantum advantage. Well, actually, it's something he's been working since a long time, but the topic has gained some kind of media attention because of the Google announcement of quantum advantage. And Jens Heiser is our world-leading expert in this topic and how to quantify complexity and how to study what do we mean by complexity, or what do we mean by quantum advantage? How can we check whether something shows this quantum advantage or not? And this is what he's going to explain to us in his talk. So please, Jens, the floor is yours.
Yeah, thanks so much. Thanks for this overly kind introduction, and in many ways, and brutal in other ways, but never mind. So thanks indeed for the kind invitation. That's great. It's great to be here. And thanks to Diego and Juanjo for all the efforts of setting up this wonderful online summer school and program that has been already running for quite a bit this week in these awkward times. I hope you're all well. But then things seem to be going better slowly, which is a true relief, I would say. Okay, so we're getting to the end of the program this week, but then we're still rather early in the field of quantum computing. It's fair to say, if one is honest about it. So hence I will take the liberty to start in very simple and basic terms and think not so much about what wonderful applications there could be ahead for quantum computers, like solving illnesses, COVID for that matter. I wish. World hunger and all that. That's not quite in store for the years to come. But instead, we'll put up a very simple and pragmatic and a careful and rigorous and at the same time still very much near-term mindset. So when we have a look at what could be called near-term quantum computing and what is called quantum advantages or quantum supremacy, even though this term has fallen in slight disfavor recently in somewhat awkward suprematist connotation. So what is at stake here is to see whether quantum devices have the potential to outperform classical computers on some tasks in the first place, no matter what. Because that seems a solid starting point to think about more practical incarnations and readings of such quantum advantages. And as Diego has already said, this has gained quite some interest. I was actually in Santa Barbara at the time when Google had made this announcement, which was like fun because literally every free shopping center newspaper and every Uber driver would be talking about this. This was really the talk of the town at the time. Okay, so it's going to be about quantum computing. We have a very near-term perspective, and quantum advantages is what we have in mind for the second part of the talk. Okay, quantum computers. So quantum computers are computers. For now, largely fictional devices, but they're computers in the sense that they have an input, a classical input, an output, a classical output, and they perform computations on these inputs. Now, the type of problems that quantum computers can solve are precisely the same problems that classical computers can solve. So notions of computability are the same as we are familiar with from the famous framework provided by Alan Turing some time ago. So a quantum computer can solve problems and of the same type as classical computers. It's not a supercomputer solving different problems, but it's a computer after all. That said, we know that there's a different computational model underlying it. So at the heart of the matter is that the single constituents are not classical systems or systems following classical laws, but quantum systems that are precisely manipulated in their quantum state. So one would have the input, one would encode it into quantum system, then manipulate the quantum state, most of the time in a unitary fashion or anticipated in a unitary fashion. And then at the end of the day, one performs a measurement to get like samples from these distributions from which one estimates the outcome of the computation. As we know, and as you've surely heard many times over this week, it's not really feasible to perform a global unitary on a large quantum register. So these unitaries are usually thought to be broken into little pieces, into quantum gates. And we know, and again, you've heard this many times, there's notions of universal gate sets that, if properly put together, would be able to approximate an arbitrary unitary to arbitrary accuracy, say, in operator. So the computation is then the quantum circuit applied to the quantum systems encoding classical information. And that's what it is. And one often says that a quantum computer performs exponentially many computations at the same time. Well, this is not entirely wrong. It's also not entirely true, for that matter. I wouldn't quite know what it would mean to have exponentially many computations running at the same time. And of course, what the measurement delivers at the end of the day are just estimates of samples. I want us to estimate the quantum state at the end. So clearly one cannot just look at all branches of a wave function, say, in an efficient manner. So in more precise terms, what is true is that one has to create entanglement along the way, or more technically put, one has to have one can't have a bounded Schmidt rank over arbitrary partitions along the way, because then one would be able to set up a tensor network that can be efficiently contracted, as we heard earlier this week, and then there would be surely no quantum advantage at the end of the day. At the same time, so there must be like entanglement, like long-range entanglement generated along the way, but if one performs the measurement, then too much entanglement is again harmful, because then the distributions become too broad and one cannot estimate the relevant quantities. One needs peak distributions. So, and this can be again made precise in quantitative. So one needs to prepare long-range entangled states and then bring them back in together in a reliable fashion. So the art form is to exploit that structure to make use of entanglement along the way and concentrate things at the end. But it is known that quantum computers are now supercomputers. They will not solve COVID for the next years and world hunger and that. Not even most mathematical problems, but some problems can be solved on a quantum computer in NP in polynomial time. So there are some problems for which one expects a speed up of quantum computers over classical computers. So you're familiar with NP. This is a complexity class. I'm sure you've heard this earlier this week. Let's recap this. This is short for non-deterministic polynomial time. It's the family of problems which can be for which there's no polynomial time algorithm known, but for which one can check the correctness of a solution efficiently in polynomial time. In slightly more fanciful words and more precisely put, this is a set of languages, that's how one puts it in the context of complexity theory, that can be verified using a procedure of the following form. So you have a polynomial time verifier down here. The verifier is given a certain input, and it's asked to decide whether the input is in the language or not. So think of the language being 3-sat. So the input is just a collection of clauses over yes, no type Boolean variables, and then you would like to decide whether it is satisfiable or not. And for this, he has access to an infinitely powerful but not necessarily trusted prover, which can provide a proof to the problem. So in case of 3-sat, this would be just the assignment of the variables in the expression, and the verifier checks the proof and sees whether all clauses are satisfied, and then accepts or rejects. There's two important properties that such a proof system should have. The first is completeness. So if the proof is in the language and the formula is satisfiable, then there should be a proof that is accepted. And it should have the soundness property, which is the property that if the input is not in the language, then whatever the prover tells the verifier is going to reject, and no proof is accepted. So that's what it is. One can generalize this a little bit and put randomness into the game and then allow the verifier to be randomized. That's perfectly meaningful, and one can relax the completeness condition a bit and say that it must not be accepted, but it's accepted with high probability. It's still pretty much the plain vanilla setting. It can be still more generalized to several rounds of interactions in so-called interactive proofs, which is highly interesting, but we will not go there. So complete here refers to the property of being able to simulate everything in the complexity class. So there's NP complete problems in P. The problems in P are the problems that can be solved in polynomial time. And the heart of the matter is that the complexity class of those problems that a quantum computer can solve in polynomial time, BQP, as one says, is including P. So it's surely more powerful than a classical computer. It stands for bounded error quantum polynomial time. It's the class of problems that are solvable on a quantum computer in polynomial time with an error probability of, say, I don't know, a quarter or so in all instances. But presumably it solves also problems that are outside P. So a quantum computer could solve some problems outside P. But in NP, nobody expects this to be it will be NP complete, but there are some problems, so one thinks, that are outside P that can be solved in polynomial time. Now, the most prominent example of this kind is, of course, the type of problem that started the whole field some time ago, Shor's algorithm. That was an ingenious insight, surely at the time, but even in retrospect, it's totally remarkable to come up with this type of argument that starts off from an insight or many insights. There's many interesting ideas coming in, but it very deeply understands what quantum computers are good at. I mean, you have the superposition principle. You can use entangled states, and this algorithm, in a very clever way, makes use of the fact that in complex vector spaces, one can very nicely use periods and also find periods of certain properties in a reliable fashion. So it went on to see that the factor of a large number can, at least with high probability, so this is meant to be true in expectation, from the period of a certain function that is set up to map the problem to a problem in number theory, and then to let the machinery run so that the problem can be solved in poly time with high probability if one finds the period of a function using the quantum Fourier transform, which is the unitary, like the quantum, well, the unitary acting on basis vectors of Hilbert spaces, just in the same way as the discrete Fourier transform would act on vectors, but on basis vectors of a complex vector space. So this does solve the problem in polynomial time. So the runtime of Shor's algorithm is of the order log n to the power of 3, compared to the best known classical algorithm. That's the same thing. So which is like exponentially worse than this, like x to the power of a similar expression. So this is the problem of factoring. That's a heart of the matter, but this has been generalized and already in the first paper to a more general hidden subgroup problem. So that kind of not only started off the field, but already understood a very deep and important class of problems that can be solved in polynomial time on a quantum computer, but not on a classical computer. And also what I said earlier is it's worth to think and meditate a bit about this, that it really exploits structure in an interesting fashion. It does create a lot of entanglement along the way. So the Schmidt rank is growing in an unbounded fashion. So there's not a simple classical tensor network algorithm that would deliver the outcome. But again, you get this same or the mentioned concentration at the end, so that you can, with high probability read of the right outcome. And then, of course, this being a problem in NP, you can check in polynomial time whether the output is right or not. So the verification problem is not really an issue. Yeah, that's great. That's exciting, and has been stimulating the field for many years, but it's not very near term. I mean, we quite painfully see this. Of course, we are happy about all these amazing developments of the last years where things are happening and people take steps to build large-scale quantum computers. We will come back to that later. That said, a full show-class fault-tolerant quantum computer is not really in store yet, so this will take some time to come. Good. So what we have are near-term computers. But before we come to that, let's maybe meditate a little bit about a type of quantum algorithms that are around. So by no means are the hidden subgroup problems the only quantum algorithms out there. Over the years, there have been a number of interesting developments. Maybe a quite interesting family of problems has been related to the idea that quantum computers are good at exponentiating structured matrices, like of the e to the power of sparse or e to the power of low rank, e to the power of sparse low rank and positive and so on, to think of algorithms that outperform classical ones if the input is appropriately encoded. That's been the principal component analysis, which is interesting, although that has been largely dequantized in the meantime. I'm happy to say more about this. Matrix inversion and linear systems, that of course already has a classical efficient algorithm, but this can be moved to log time if the input is provided in the right and appropriate fashion. Algorithms for spectral analysis, semi-definite programming, that's at the heart of many, well, that's one of the cornerstones of convex optimization that again allow for a quantum improvement in the long run. That's again exciting, but also not very near term. So at the heart of the matter is the question what we can do with small, noisy, warm and wet, maybe not wet, but warm and noisy quantum computers of the type as we have them. So we presently only have small and noisy quantum computers, but we should not really see the glass as being half empty, but half full, because we have small and noisy quantum computers. That's an exciting development. It's new, it's fresh, and it's quite exciting that over the last years, protagonists have kind of, well, put a lot of money into their hands and made significant efforts of trying to build machines that live up to the promises of the field, because for most of the time, quantum computing has been a stimulating theoretical idea that has been extremely inspiring and interesting, but the idea of realizing such machines is comparably new. There's, of course, the IBM 53-qubit superconducting device. There's work done by Rigetti along similar lines. We know of Google's 53 or 52, one qubit is broken, or 72 bristlecone qubit devices. This actually was fun, if I may say so. We had a wonderful collaboration with our friends at Google over the last years, and well, it asked me if interested, and sat down to basically calibrate the Sycamore chip and learn the Hamiltonian from data, or walk the chip and see what Hamiltonian they actually have compared to the anticipated Hamiltonian, what they think they have, and it's hilarious. You can really walk the chip and see like dark corners and wonderful areas and so on. It works with high precision, but there's a lot to be learned and said about this. And we made the joint effort of learning the Hamiltonian in the lab, bringing together ideas of a bit of machine learning type ideas and super resolution ideas. I'm happy to say more about this. There's also the efforts of PsiQuantum, which are optical, and they're more in stealth mode still. But again, it seems fair to say that a lot is happening in order to realize or set out to realize machines that live up to the promises. These are small, but there's talk of significantly larger systems. Maybe I shouldn't contribute to speculating how large that is, and I know what my friends are saying in these companies like at Google or at PsiQuantum, but maybe that's not something I should express here in public, in the public realm. But things seem to be going well, and it's surely an interesting state of affairs. So what can you do with small-scale devices? Now, Jacob Biamonte has already given you a lecture. He's a leading expert on this field. So I will reiterate some things. Never underestimate the charm of hearing something you already know, but it is interesting and important. So we should emphasize that most of the applications that we have in mind for the years to come are of a variational type where there's a quantum computer in the center, a circuit that has lots of knobs, control parameters, where you do things, you prepare, you do something, you measure, you get outcomes, and then there's a bigger classical algorithm around that would do things and would update the control parameters and would iterate things so that the quantum algorithm is just a part of a bigger system, which makes perfect sense because quantum resources are so painfully expensive and precious, whereas classical resources are abundantly available. That's called a hybrid algorithm, although anyway, if you think about it, every algorithm is a hybrid approach. Even Shor's algorithm, of course, is a classical algorithm with a cute quantum subroutine calling cute quantum oracles, as you must know. If you think of topological quantum error correction on top of that and decoding, it's clear that most of the time, supercomputers are running and doing all kinds of stuff with a bit of quantum in the middle. So the term hybrid quantum computing is exciting and interesting. It's a bit of a misnomer because anything you will ever do with a quantum computer will, at the end of the day, be a hybrid algorithm in some way. That said, you really mean a non-quantum error-corrected, non-topological, non-fault-tolerant device that has knobs where you do things and update in a very near-term fashion. That's what is meant by a hybrid algorithm. And heuristically, it has a very encouraging performance, it seems fair to say. There's some reviews given down here that are very much worth reading in this context. So the most basic, plain vanilla reading of this is the so-called variational quantum eigensolver. This is, well, it's a family of problems that basically does nothing than implementing a reading of the variational principle in quantum mechanics. So you have a set of states and you parameterize this set of states by some knobs. It's a parameterized quantum circuit. And then you try to minimize the state that you have within the family of parameterized circuit to minimize the energy. This being a subset in Hilbert space, this clearly gives an upper bound over for the ground set energy if H is a real Hamiltonian or a fictitious Hamiltonian that encodes a real Hamiltonian. This has applications in condensed matter and quantum chemistry. So one would set up a circuit and would also think of a Hamiltonian so that the quantum circuit would, in a variational fashion, minimize the state over the variational set, and then you get good bounds to the respective ground set energies that hopefully improve upon classical approaches. This is a delicate matter. It has heuristically very encouraging performance. Of course, it comes along with all kinds of tricky bits and problems. To start with, it's not so obvious how to pick a good variational set. One should exploit symmetries as much as you can. It's also clear that it makes no sense to try to approximate all states, which is well defined. You can think of so-called spherical designs, K-designs, that would be able to approximate arbitrary states in a very precise fashion. That said, a moment of thought reveals that if you do that, then you are basically not approximating any state very well, or most states not very well. So you have to think harder what a good ansatz is. People have been thinking about breaking symmetries by hand, like even parity of super selection rule symmetries in Fermi systems to have a better variational landscape. It's tricky. There's a lot of good research going in, because one should be aware of the fact that it's not only about what states you can capture, so the so-called question of expressivity, but also about how to optimize over these guys, over these settings. And, well, I mean, to warn you, this problem has been identified to be NP-hard in worst case complexity, even if you do just a variation over a simple free fermionic system. So the optimization problem is a hard problem. That said, that doesn't mean that it will not work heuristically in many settings, but one has to work hard, and many thoughts have to go in. So the best way of setting up such a variation quantum eigensolver is not yet out there, it seems fair to say. A more sophisticated way of looking at this is what is called the quantum approximate optimization algorithm, which is in some way, well, very simple or sophisticated, depending on how you want to put it. It's a variational quantum algorithm that is designed to find good approximations of combinatorial optimization problems, which are, again, NP-hard in worst case complexity. So nobody expects a polytime solution to this type of problem, but it could be true that one, for some structured instances, finds a good approximation that outperforms the available approximations in the classical domain. For example, you can think of combinatorial optimization problems such as max-cut and try to determine the binary string that maximizes a given classical objective function that encodes the problem. And the aim is to find a string that achieves a desired approximation ratio of the achieved value of the objective function over the optimal value. And what one does is one basically takes this problem and encodes it into a Hamiltonian, so that the whole thing is set up as a variation quantum circuit where one calls the Hamiltonian with variational parameters and kicks the guy out of the basis with a parameterized circuit involving Paulis, and would again apply the encoded Hamiltonian, and does this in many rounds of Quawa if you want, so that you would, upon variationally optimizing these circuits, find a good energy of this hypothetical Hamiltonian, aka find a good approximation of the optimization problem that's being encoded in this Hamiltonian. This is a wonderful idea. It's basically like a quantum-kicked way of doing an algorithm that is in some ways a bit resembling, I don't know, metropolis sampling. Well, there's more to say about this, but I will not. Where there's hope that you can go beyond the capabilities of classical computers. It's not yet quite clear what that is. I think Jakob has said something about this. It's not so well understood beyond a single layer, although that would be important. Single layers are pretty well understood, but they're also not so powerful. There's an increasing body of heuristic literature on this. There's also very cute, exciting, rigorous steps. Like there was this beautiful paper by Matt Hastings, who writes theorems like he skis, which I have painfully witnessed some time ago, where he had this wonderful idea of how to find a classical simulation algorithm on Max 3 Lin 2, some combinatorial optimization problem where he has a polytime classical optimization like algorithm, that solves the problem in polytime. So that's interesting because it delineates the boundary between quantum and classical. So it's good to know how far this goes, because then it's clearer where one can go. Now, of course, one of the big applications of near-term quantum computing, so they say, is in learning tasks. I must say that this is something I'm personally extremely interested in these days. What's at stake for quantum-assisted machine learning? And this comes in many flavors and forms. I will not go into too much detail, although I regret this, because it's an interesting field and there is a lot in store, and there could be many ways in which quantum devices could outperform classical ones over machine learning tasks, which can mean many things. A computational advantage in terms of computational complexity, or sampling or one in terms of sampling complexity. You can think of different data axes of sample axis of just having classical data or statistical query axis or whatnot. There's many ways you can think of the problem and many readings. There's a lot to say about this. So on the highest level, there's a lot of heuristic work, which is interesting, that seems to show the potential of looking at this idea. On rigorous grounds, that's more my specialty of trying to see what's really in store here. One can think along the lines of what like parameterized quantum circuits can do at the end of the day as models for machine learning. For example, that's something we looked at of parameterized quantum circuits that encode data into a parameterized quantum circuit that has a data input and a trainable unitary in the circuit, where the question is how one sets this up and how one can prove, say, generalization bounds that give performance promises on unseen data that respect the data encoding problem of getting the data into the machine that has been overlooked. Or ask the question, what is in store for quantum learning, quantum machine learning? We had the insight that in Park distribution learning, so probably approximately correct learning, which means given samples from a generator, you want with high probability, so probably approximately correct spit out samples. So have a generator that spits out samples that is close, say, in the Kullback-Leibniz divergence to the original setting. That's a very clean way of thinking about a learning task, where the interesting insight is that these guys can have an exponential separation. They can be exponentially more powerful, not in sample complexity, but in computational complexity to classical machines. That's very encouraging. So there is a case, there is quantum machine learning. You can think of problems that does something, even in the way of having exponential separations. That's the good news. The bad news is that this is not very NISQI yet. This is a true quantum algorithm. It's not living up to the expectations that David has, that Jacob has, for example, mentioned. And also, it makes use of, and it's a long and winding proof, and I will not go into detail, but at the lowest end of the hierarchy, it's basically running like looks at one-way functions that break a certain hierarchy, and the discrete log algorithm is at the heart of the matter. So it uses a type of structure that is much familiar with in non-learning type quantum algorithms. So it's a meaningful concept class. There's no cheating. It's classical input, classical output. So there's no funny encoding happening and so on. It's a proper separation. It's a proper encoding. There's classical data that you can write down on a piece of paper that you feed in. I mean, it's completely honest and fine. And there is an exponential separation. Great. But as also the recent IBM work shows, one does seem to rely on structures that are familiar in quantum algorithms already. So it's not so clear how one can go beyond that. And when I refer to the IBM work, that it did work on quantum kernels, but again, at the heart of the matter, what they do is they rely on quantum algorithms outside the learning context to see that there's a learning advantage, but it would be good to have better and more powerful instruments here. So that's something we are quite concerned with these days. We are about to write a paper on quantum and classical Puck learning of Born machines or of parameterized of quantum circuits, but well, this will come out later, and I will maybe not go so much into detail. Maybe let's finish the first round and have a break a bit earlier to have more time for the second round, and also have time for questions at the end, to meditate a little bit on the problem in classical quantum hybrid algorithms, that one should be aware of the fact that whatever you do, there will be some classical algorithm running. There's a loss function that needs to be optimized, and one has to find parameters that optimize the respective variables in one way or the other. That's not a detail, but that's at the heart of the matter in any quantum classical hybrid algorithm, because one has to find a good solution of doing something with the device by tuning the parameters appropriately, even though, again, this is a NP-hard problem if properly formulated as a decision problem in worst case complexity. But what one commonly does, and that's something that also Jacob has hinted at, is one has the cost function and tries to minimize the cost function based on outputs that one anyway has in the device. So one estimates the gradient from data to get an update for the variational parameters. So one goes into the lab or asks others to go into the lab, performs a measurement, and then from these data tries to estimate the gradient for getting an update. So for this, what can one do? One estimates expectation values. So one does many runs of the same setting and then gets expectation values of observables. From those, gets an expression for the gradient, and then one would perform the appropriate gradient update or first order method update for the variational parameters. This is great. It's extremely expensive. So there's some shortcuts. What one can and should exploit is something that's called a parameter shift rule. That's in some way like a symmetry in the problems. So a quantum circuit would satisfy a k-term shift rule if basically the some derivatives of expectation values of observables can be written as linear combinations of other observables of the same control parameters, but evaluated at different control parameters. And this is a very nice property because then you can use that symmetry if you want to more cheaply estimate the gradient from data, because that's a very costly and heavy fashion. So again, then one estimates the gradient for getting the update. This is great. One can also find general gradient rules. This is a bit of a topic that people are interested in, how to improve this, how to use combination of first and second order methods, of how natural gradients come in. This is a field in its own right of thinking about the classical control in quantum classical hybrid algorithms. It's interesting, and the last word has not been spoken yet. There's maybe only one little thing that I would like to mention here, which is that this can be improved by stochastic gradient methods, actually, which is very simple, because it just means that you go into the same lab, you perform the same measurement, and you do the same thing, except that you are not running the same prescription many times, or the abstraction arbitrarily infinitely many times to get the expectation value, but that's k-shot measurements. This is important because in some settings, I've been talking to Emmanuel Bloch this morning, in these cold atomic settings, one measurement takes 30 seconds. And you don't want to do a million measurements on a device where one click, one shot costs 30 seconds. Our life is too short for that. So it's good to think of methods where you do not have to have access to expectation values, but just raw data to do things in the light of also the complexity theoretic insights I had mentioned earlier, that this is a hard problem, but I will not go into that. So what one does, go into the same lab, but don't do infinite repetitions of the measurement, but n-shot measurements, and measure n times the observable, so that you get a faithful estimator of the expectation value in the limit of arbitrarily many repetitions. And and this works in fact very well. It's the same type of data. You go into the same lab, but you can still prove convergence in the sense that if you're at an optimal point, you find that there's an epsilon neighborhood around that point that would allow for an exponentially fast convergence in n in the number of measurements you take to get a convergence to the optimal point, and then estimate the gradient. Here we have this kind of doubly stochastic gradient method if you want, because it's a stochastic gradient method where the stochasticity in parts comes from the finitely many repetitions of the same measurement, which is one of the many recent developments along the lines of finding good classical control algorithms of moving forward. But this is almost a field in its own right. You can warm start, you can think of natural gradients, you can think of higher order methods and so on, exploit structure. So this is actually quite interesting to think how you would best control a classical control algorithm for a quantum variational circuit. Again, I refer partially to Jacob Biamonte because these are interesting problems to work on. Good. Which brings me to the end of the first part. Before we move on to quantum simulators, to quantum devices that do something interesting, and to the question of how to achieve quantum advantages. So maybe let's maybe do a 5-minute break or so, and then we reconvene, and we have a slightly longer second part, and then we would have time for questions at the end and meditate a little bit about what this all means, where one could go, and what interesting open questions are. Is this good?
Okay, yes, great, yes.
Wonderful.
Yeah.
Good. Yeah, so then let's have a bit of a fresh air. I get a coffee, and then we reconvene.
Okay.
See you in 5 minutes.
Yeah, thank you.
See you.
So, welcome back. Shall we continue? Is that a good moment, or shall I wait?
Just 1 minute, maybe, because we'll have 45.
Good. Yeah.
Okay, we were 25 something. Yeah, maybe we can continue.
Yes, wonderful. Welcome back. Good to see you again, or good to not see you again. I would love to see you. That's all we have. But let's look at near-term quantum simulators and quantum devices that are even more near-term, say, than what we had in mind earlier. It's not even near-term, but past-term, if you want. So the question that's at the heart of all that, of any of this, is whether we can have realistic hope that noisy, existing, or at least realistic quantum devices offer a speed up over classical computers in one way or the other. So you would perform some measurement, some experiment, and you get data, and then you feed the data into a classical computer, and then you would like to say that, oh, great, this is something interesting. This is providing a speed up over classical computers. Then the light becomes green, or there's no speed up and the light would be red. So can we have realistic hope of that kind? If the answer is no, then that would be quite sad. There would be little point in pursuing further activities along these lines. So we better have some hopes that this is realistic. If yes, that's great. It may not be the end of the road, but it's surely a nice milestone to know that there is something that quantum machines can do computationally that is beyond what is in store for classical computers or classical supercomputers, for that matter. So what are quantum devices? This can mean many things. It can not only mean quantum computers in the sense as we had spoken about them earlier, but also notions of, say, quantum simulators, if you want. So devices that, if you want, are the dirty brothers of quantum computers, in the sense that they would be allowing less control. They would not be quite universal devices. You cannot run arbitrary computations on them, but they exist and they are large. So there's some devices, some quantum simulators with, say, 10,000 sites, say with cold atoms and optical lattices. You can easily have 10,000 sites, aka 10,000 atoms, aka 10,000 hyperfine levels, aka 10,000 qubits. So these are systems where in some way the asymptotic limit is already built in. I don't want to bore you. I tend to cite Ian Wormsley in that context, who once gave a wonderful talk in Oxford on some beautiful protocol he had implemented when he was still there. And then some smart-ass student said, oh, that's great, but can you also do this in an asymptotic limit? And then Ian said so nicely, we are experimentalists. We are not asymptotic people. But this is not quite the case here. So this is quite asymptotic, and you have less control. But for what you have, you can go to quite large system size and can perform interesting experiments along these lines. So in this fashion, one can look at ground state problems, say dynamical problems that are sometimes dubbed quenches. So you just look at the natural time evolution that's being generated by local Hamiltonians, or you can think of slow evolutions that's reminiscent of adiabatic quantum computer, or a bit beyond when you think of Kibble-Zurich type settings, where you are basically no longer fully adiabatic, but close to critical points. But these are the types of problems that quantum simulators are natively often performing. So this is a problem that I like to state in this context, which is already not so young anymore. It was a kind of a baby step at the time, but I think an interesting baby step in a good direction, where the Emanuel Bloch lab in Garching looked at questions of equilibration and thermalization of atoms in optical superlattices, where we provided the theory support, which is a long story and embedded in a wide context, and that's physically meaningful in the sense that you basically measure out how the approach to the ensembles in statistical mechanics is actually dynamically happening. There's a lot to say about this. For the purposes of this lecture, it's maybe most interesting to just say that it's performing some quantum simulation in time, and one can look at settings of the type where you have a lattice, say one-dimensional, although that's embedded in 3D, but never mind. So for our purposes, it's a one-dimensional system. You have like 0, 1, 0, 1, 0, 1, like 0 atom prepared initially. It's charge density wave, as people say. And then you would look at the full interacting many-body dynamics generated by a Bose-Hubbard Hamiltonian in the deeply interacting regime. And then you can look, for example, as a function of time, at the number of odd particles per side. So initially, there are no odd particles because they all sit in the even sides. But then there will be some complicated or not so complicated, just for yourself, like some dynamics happening, and then something is going on. And for very long times, there's just half a particle sitting there because the 0, 1 would be equilibrating along the way to balance out in the long. So this is an experiment that can be done, that has been done using optical superlattices. If interested, ask me about what that is, but it offers a nice level of control to the type of system. And this picture here shows, among many plots of that kind, the number of odd particles as a function of time, where the blobs are the experimental data obtained in the lab. That said, this picture not only shows these experimental data, but also the classical resimulation of the same type of problem. It's not a fit, but it's a resimulation on the same system's parameters, and it's not just some classical algorithm or some data, but it was the best known classical algorithm at the time. It's some variant of the TEBD algorithm as a variational method over matrix product states. It was run on the fastest computer the German taxpayer could afford. That's the Jülich Supercomputing Center, which it still is. It's still the fastest computer in Germany, to my knowledge. And you would have like 5 weeks of runtime per plot of this kind. And so that's kind of the upper limit of a reasonable numerical computation of a kind, because otherwise it's not published by a PhD student. And that's the data. That said, these data are very precise, that if you want even rigorous for short times, you can find error bounds, only that they will not go on for very long times for the build-up of entanglement in this state. And you can do this for short times, but there's no algorithm based on matrix product state that would go to long times, because there's an exponential blow-up of the bond dimension. That said, there cannot even be any algorithm of that kind, because that's a complete problem, looking at the locally generated Hamiltonian dynamics, but never mind. The thing is, you run the classical algorithm, and then there's a barrier you can no longer overcome with the classical supercomputer. But the experiment runs on. Why would nature care what we can do on our classical computer? So this generates the interesting situation that you can run a quantum simulation and a classical simulation on the same type of problem, but the classical simulation is somewhere stopping, and the quantum machine is in some way outperforming the classical machine, and the classical data can be used to build trust in the correctness of the quantum data at the end of the day. So this is a bit of a baby problem. It's also not a super interesting graph for that matter, but it's interesting, and it's also quite thought-provoking, because yes, it's not very interesting. I mean, of course it's very interesting, but it's not very complicated, say. But it's also mind-sharpening in the sense that people have been trying to look at mean field approaches fitting this. Yes, that's possible, but one has to be aware of the fact that the fitting involves an estimate how the interaction comes into play, and that's a priori knowledge that it would not have without the quantum simulation. So it's not so much about a fit in retrospect, but you want predictive power for what comes in experiments. It's all about prediction. That's a different matter. What is more, it's not about one plot, but about a family of plots or functional dependence on knobs to plots, and that's again harder to reproduce. So it is what it is, but one should be aware of the fact that this type of problem is already physically meaningful and interesting. It's addressing physically important problems, and in some baby way, already like 9 years ago, quantum simulators, large-scale devices, outperformed the best available classical algorithms run on classical supercomputers at the time. So short times can be efficiently simulated, long times not. If one is not happy about this, one can also go to more sophisticated kinds, problems of this kind. So again, together with the same team, we looked at Kibble-Zurek type mechanisms. Don't get me going. It's again physically interesting, where one can go into the lab and perform experiments in 1D and 2D, where in 1D, also classically, everything can be said in all glory and detail as much as you want. In 2D, not. For, again, the entanglement growth problem. But the move from 1D to 2D in the experiment is like extremely simple. It's just a change of the confinement. So here, 1D systems can be efficiently simulated classically, 2D not, but they are much accessible in the quantum realm. And again, there was follow-up work by the same team on many-body localization, where again in 2 dimensions this is perfectly available and possible. So these are baby steps, but in an interesting direction, in that it's sometimes underappreciated that already today, or not today, I mean, this is like some time ago already, it's already in the past, there have been exciting experiments that probe interesting physics, like of equilibration and the emergence of statistical ensembles in physics, which is, I find, an interesting physics question. The question of Kibble-Zurek mechanisms of approaching criticality, or whether there's universality in the complex plane, if you want. So how far the universality conjecture can be pushed to tackle and address non-equilibrium situations, or questions of how interaction and disorder come together in many-body localization. It's interesting in its own right. And these questions can be addressed, and in a way where the best known algorithms would not be able to make predictions on the same problem. And that's great. In some way, that is already a physical quantum advantage. So depending on who you ask, they're quite happy, say, what are you talking about? That is a quantum advantage. We have a machine. I can do something. I find the outcome interesting. And I cannot classically resimulate this. So that's all I want. Well, the physicist heart in me says, yeah, that's a point. The computer scientist / applied mathematician in me is a bit more skeptical, in that, yes, it's good to ground this in the language of computer science. So to be safe against a lack of imagination, one would like to prove the hardness of the task in some kind of complexity theoretic sense, in a similar way as we talked about complexity classes at the very beginning of the lecture. There's a point in that even in my group, we've been working on improving on time evolution algorithms, and then one can indeed push this further and still have an efficient classical algorithm. Ask me if interested about this, but one can push things. This will not go forever, because then BQP would collapse with P, but for arbitrary local Hamiltonians, that is. But it would be good to have a stronger statement and ground this in the language of computational complexity. So again, can we hope noisy, realistic quantum devices provide a speed up over classical computers, and you want to be safe against a lack of imagination and try to prove this in some complexity theoretic sense. Which leads us to the quest for quantum advantages of a kind. So this I've already put up. What we want to perform measurements and then learn something from and about the measurements, and what is a reasonable setting of this kind. Of course, we can think of some problems that are in BQP but outside NP, like in Shor's factoring algorithm, that surely gives a quantum advantage of that type, because we run the machine, we do factoring of 15. We get the outcome 3 and 3. Is that right? No. We get 3 and 5. Is that right? Yeah, wonderful. We've checked it. So clearly, problems in NP would be doing the job, but that's not really in store for now. So we would like to look at some problem outside NP that's more realistic, more feasible, but for which we can still say something interesting. So again, when we think of testing that, or think of like a computational bell test, if you want, when we ask whether nature permits computations that are exponentially faster than probabilistic Turing machines, Shor's algorithm is a good candidate because you would perform the algorithm, we get data, we check the correctness of the outcome. If yes, you would say, great, we've done it. If no, we would say, yeah, we have to try harder. But this would be clearly a quantum advantage or supremacy experiment, if you want. So any problem in NP, like factoring, would be a wonderful candidate to do that. That's great in theory speak, but as we know, that's not quite what we have in store today. What we have are these wonderful devices as shown here. I'm sure you've seen these pictures many times before. That's like the Google machine, or the fridge of the Google machine if you want. And you want to perform something simpler that's easier to tackle. So in the perfect world, you would like to have something like single round, classical data. So just one measurement, and then you do something with it. No conditioning, no feedback, no circuits, but just do something, and then you get data. And get classical data just from a Born machine type thing, like from a circuit where you measure, you get data, and you talk about this. And it should be a small quantum device, not, well, small, what a small, but at least not huge, but meaningfully large, that you have hopes to realize this in an experiment. Now, a couple of proposals have been made along these lines. Maybe the most prominent one is this one here, where one goes into the lab, and that's also what the Google team has done, and performs what is called a random circuit. What is a random circuit? A random circuit is a circuit that's random, so that you would have some gate set, yeah, for example, a universal gate set. Like, for example, you pick Haar random gates, and you would apply Haar random gates, and then you would build up a circuit of it. This kept us quite busy. You might have seen our work on linear growth of complexity of random quantum circuits. That's something I'm super happy with. Ask me about what this is about. This is actually quite cool. I will not say anything about this, but there's a lot of, it's quite meaningful to think of random quantum circuits that take a universal gate set, and then you do something and you measure at the end of the day. That's also called a Born machine for that matter, and that's quite meaningful and experimentally accessible in several settings. In fact, in the Google experiment, it was done like that, except it was not a Haar random circuit, but they had a native interacting gate that was sitting there. You could switch on, and then a local Pauli gate that had an element of randomness. It's very much related to this picture here because it's still a universal gate set, and you can think of how quickly you would like have a certain mixing property, like have a unitary design property in fanciful terms, if you apply a random circuit of this fashion. But that's a candidate. You perform a random circuit, you measure, and then you get data. And the question is, can you do this also on a classical computer in the same fashion? Now, the insight is such sampling tasks, and if you think about this, every experiment in quantum physics is ultimately a sampling task. So you're just saying, I take data seriously, native data, as I get them. I'm not trying to estimate expectation values, but you just call the experimentalist and say, send me the raw data and give me the full thing, the full material, and then I will do something with it. That's a sampling task. And that is very natural for a quantum computer or a quantum device. In fact, that's the raw data you get natively. But this turns out to be hard for classical computers. And that's quite interesting. This is not necessarily an easy task on classical computers. Another one is instantaneous quantum polynomial circuits. So IQP circuits, they're commuting even. That looks almost classical, but still you cannot on a classical computer you cannot sample on a classical computer from a distribution that's close to the IQP circuit distribution in polynomial time. Then boson sampling is yet another flavor thereof, which is not working in qubit space, not a finite dimensional system, but in mode space, where you're basically thinking of optical modes. You go into the lab, you have bosonic modes, and you prepare systems like photon, 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 nothing, nothing, nothing as a preparation. And then you would perform a circuit. And performing a circuit would mean that you perform a unitary mode transformation, so that linearly or unitarily transforms bosonic modes to a new set of bosonic modes. For example, in a Haar-random fashion, which can again be built up from beam splitters and phase shifters. But now the Hilbert space representation is the if you want the metaplectic representation thereof in fanciful terms, that would be the Hilbert space representation of that mode transformation. What you ultimately do is you just do a sequence of beam splitters and phase shifters in mode space, and then you're manipulating the stage that comes out, and then you sample the photon number at the end of the day. That was also historically one of the early sampling experiments or conceived sampling experiments of the kind. Now, this is like a quantum golden board. Again, sampling tasks are natural for quantum computers, but are hard on classical computers. Let's do that experiment. So I did this. Could you see this? 10110, 01011, and so on. The upshot is that you can realize such experiments of IQP circuits, random circuit sampling, boson sampling in the lab, but sampling from a distribution that's close to this one that you get in this fashion, more precisely in the L1 norm, so in the total variation distance, is computationally hard with high probability over the circuits if they're sufficiently long. So for the boson sampling, you would have to scale the number of modes appropriately with the number of photons coming in, like 1 is the other to the power 5, and you pick the circuit Haar-random, and then it's hard in the sense that you would get a collapse of the polynomial hierarchy to the third level if you found a classical simulation algorithm that approximates that distribution up to a constant error in the total variation distance. Note, constant error, that's a bit tricky because it's more and more demanding for higher system sizes, but larger system size. But it's interesting that sampling is, in this sense, hard on classical computers up to a meaningful like constant error in the total variation distance, which makes perfect sense, but is perfectly classically quantumly possible, and Canon has been done in a prominent fashion. So indeed, Google has done it. They say that if it achieved quantum supremacy breakthrough over classical computers, this was this amazing breakthrough from 2 years ago. It's an immensely cited paper where they did random circuit sampling and looked at this, and also looked at several verification techniques. There was also other press on IBM where IBM disagrees. That's a healthy process of like clarifying the mind of what it really means to have a quantum advantage of that type. But it should be clear that these experiments do something that is presumably hard on classical computers, and in some ways can even have a body of rigorous work behind that clarifies what's going on in a precise fashion, and we come to that later in the talk. In fact, that's all I will say for the rest of the talk, because I would like to keep it short to have time for some thinking and meditation at the end. So not only can this random circuit sampling be done, and has been done prominently by Google, our friends there, but also in the optical setting. There was just work by Tiawei Pan in China on Gaussian boson sampling. That's a variant of this boson sampling I mentioned earlier, where again, they could go to very large system sizes in the photonic setting, not so much in the superconducting setting, but that's again extremely exciting, where again, one would have some device of a sampling type, no conditioning, no adaptation, no proper circuit, no algorithm that's really solving something, but already some milestone type setting where a quantum advantage has been reached in sampling. That's wonderful, and that's exciting, and this is a really nice step in a very motivating direction, it seems fair to say. Good, but there's some fine print. One thing is how one finds out whether one has done the right thing. And there's some things to be said about this. I'm not going into the interesting discussion of how to do like linear cross-entropy benchmarking, so on, what that has been implemented, what it precisely says. That's interesting, but rather say, what would be the most stringent way of a verification that one would like to see in such sampling experiments, which would be basically that you go into the lab and you look at data from quantum devices and do what is called black box certification, so like a device-independent reading of that. So you really perform an experiment, you get data, and what I mean by this is you proudly perform some random circuit sampling or some boson sampling, some sampling experiment of that kind, you get data, and based on these data you say, I've done it. Green light, I've been successful, or red light, I've not been successful. That's what black box verification is. So based on data alone and the input to the algorithm, you would have access to the unitary that's being implemented. So in this sense, it's fair, but you would like to see based on the data whether you've been right or not. And that's meaningful because you want to see that you have not only done the experiment, but that you've also been successful in doing the experiment. That's always good to know and good to hear. That's what black box verification is about. Again, I mentioned this earlier, so our obsession in the last weeks and months has been to look at Puck learning of the output of random circuits or of Bohr machines of this kind. That's interesting, but that's a bit of a different flavor, although quite related to this. Here we just want to say, yes, I've done it, green light, or I have not done it, work harder, but it has been a good journey. Let's put this in slightly more fanciful terms or more precise terms. What I mean is just the same. You look at data and you check right or not. A slightly more fanciful way of saying the same thing would be that you have a black box certification test with some sample complexity M, a number of samples, is some algorithm that takes inputs of length M, or M samples thereof to 1 bit, with the property that if you are sampling from precisely the right distribution, then the probability of accepting would be like larger than 2/3 or so. Whereas if you are more than epsilon away in the total variation distance, then the probability of accepting would be smaller than 1/3. That's really the kind of weak membership reading of the same thing, that you're really precise, you say yes, and if you're a bit off, you're saying no with high probability, but this way of having this total variation distance is meaningful to the errors in the problem that you might have. That's a fair and mathematically sound way of saying the same thing, that you are just checking from data alone whether you've been right or not. And this would be sample efficient if M is a polynomial in the number of n. Note that this is all about sampling complexity and not about computational complexity. So you can grant the machine unlimited and even infinite computational power. Never mind, you just want to say how many samples I have. Life is short, you can always ever have polynomially many samples. And then you say, take the samples, am I right? Green light, I'm not right, red light, and that's all I have and would like to see. Now there's a wonderful machinery by these like by these brothers here. So one of these interesting families. There's also the Bernoulli family. There's the Horeckis. There's the Kerns. I mean, there's lots of families of that kind. These are actually brothers also who did seminal work here. And that's a hilarious and very exciting mathematical machinery. And it's indeed quite clear how one could assess whether black box verification is possible based on the distribution. That's a property of the distribution to be verified. It also matters how wide the distribution is and whether you have concentration or anti-concentration in the setting, whether you can do black box verification from polynomially many samples. Now, at the heart of the mathematical machinery is the most hilarious norm I've seen in my life. It's the P min max minus epsilon 2/3 norm, which is take the distribution, you chop off the largest element of the distribution, then you take the epsilon and sum up the smallest elements until you get the value epsilon. As a tail, you rip it off, and then you have the chunk in the middle, and this guy you take, and you take the Renyi 2/3 norm of that. I mean, you can't make that up, but that's the figure of merit you need to think about in this context. And then if this is appropriate, then you can do black box verification. And if you sit down and do the math and work hard, you find that for boson sampling, IQP circuits, random circuit sampling, there is no way to do black box verification from poly-many samples. For some, there is, but not for these distributions. In fact, interestingly, it's even the anti-concentration that matters, or the very property that makes it hard for the classical computer to sample from this is also the same property, more or less, to not be able to do black box verification, which is an interesting state of affairs. So you have to resort to other methods that prove the plausibility or the correctness of the implementation as such. But in a device-independent fashion, in this sense, it's not possible. So it's a bit ironic that you can do something great and do whatever IQP circuits, random circuit sampling, and then say, oh, but prove that the data are correct. And this is provably not possible, that just by looking at the data alone, you will not see whether the outcome is correct. And that's all there is. Now, take it what it is. I mean, there's no need to panic. It's also it's interesting to see how people react to this insight. Some people say, oh, that's bad. I cannot verify the correctness of any of these sampling experiments. That's the end of it. Others say, oh, I mean, please. I mean, I didn't expect this to be true. In particular, a common prejudice, and that's particularly common in the physics context, is that, oh, it is what it is. In order to be able to verify a quantum simulation, or a quantum device for that matter, one needs to be able to efficiently simulate it. If you can, you check correctness. If you cannot, you cannot. And that's the end of the day. That's common and much expressed. Anybody, I mean, Diego is much involved in quantum simulation activities. That's a slide that's often put up in quantum simulation talks. That's what it is. But again, mathematically speaking, there's no efficient black box verification test for these sampling experiments, even if you grant the computer exponential computational capabilities, which is an interesting thing in its own. Okay, beyond black boxes, let's come to the end, or the last point of my presentation, or the journey that we are having today. Has been interesting so far. So let's look at a simple near-term quantum advantage scheme. So what is this? What is simple? What is near-term? So this was already some 2.5 years ago, when we thought, okay, great. Can we make it a race? Can we think of the simplest conceivable scheme that shows a quantum advantage or quantum supremacy, for that matter? And we were working hard and harder, and had a simpler scheme and a yet simpler scheme, and we wanted to see how far you can push it to make it increasingly simple and interesting. What we wanted is to have a simple Hamiltonian quantum simulation, or a flavor of a Hamiltonian quantum simulation, at least from the perspective of a physical necessity in the lab. But it should still come along with hardness proofs with an L1 norm error in the right sense. And we cooked up a couple of schemes of that type. And I keep it short. I will not go into detail. There were some quasi-periodic, some translation variant models. I will only say a few words on one of these models, because that's maybe the most compelling one on a random thing. It's really extremely simple. And that's my last point. I will also release you earlier to lunch, as I said, because and we keep some time for meditation. What it is it's a scheme of qubits on a square lattice, on a 2-dimensional square lattice. And there's basically 3 steps happening. Yeah, and they're idiotically simple. The first one is you prepare states. Before you have to prepare some quantum state. And the state you have is not a complicated, entangled state. It's not a topological state. It's not a long-range, blah, blah, order parameter state. It's a product state. No entanglement, no nothing. It's just a product state of qubits on the lattice. It hardly gets any easier. This scheme has some randomness in that you either prepare 0 or some tilted basis, But there's also other schemes that have no randomness whatsoever. But that's what it is. But it's a product state. No entanglement, no correlations. It's a product state that you have in the lab. This is the abstract description. If you want, you can think of the analogy of disordered optical lattice systems. See this as the ground state of an optical lattice. And this has been done. This can be realized. But well, think about these terms. Think about this in terms as you want. But it would be just a product state of qubits arranged in a cubic lattice. Then you perform a quantum evolution with the simplest Hamiltonian I can imagine. And the simplest Hamiltonian I can imagine is the plain vanilla nearest neighbor Ising Hamiltonian. No long-range stuff, not even non-commuting terms. It's just a classical Hamiltonian if you want. It's a nearest neighbor ZZ Hamiltonian. I mean, that's the simplest Hamiltonian I'm aware of. Please tell me if you know of a simpler many-body Hamiltonian, but that's the 101 Hamiltonian that you can do in any setting, and you don't apply this for long times, but only for 1 unit of time. Yeah, switch it on and off, not for long time, but just 1 unit of time, and then you're there. And you evolve it in time. Or equivalent, you would do a unit time step of this unit depth Hamiltonian, a unit depth circuit. Never mind. In this Hamiltonian analogy, you would switch on the Hamiltonian, and that's it. That's as simple as it gets. I mean, note that this is a commuting Hamiltonian. So all terms commute. So clearly, this doesn't generate any entanglement or any long-range entanglement in the system. Everybody sees only the neighbor. It's borderline classical, right? I mean, all terms are commuting, and it's just one time. So everybody sees the neighbor, and that's it. It's a unit depth quantum circuit. Yeah, so that's what you do. 1 time step of a commuting classical Hamiltonian. Again, if you want to keep in this analogy of optical lattices, which is a nice mind game, this is not only possible in cold atoms, but it was in fact one of the early experiments in this field. In fact, there's here Greiner, who's now in Harvard, Hensch, who in the meantime won the Nobel Prize, Bloch, who is in Garching, all on the same paper. With these controlled collisions in hyperfine levels, this can be done and has been a way of preparing these states or these Hamiltonians. It's the basis of the cluster states that came out later that gave rise to one-way quantum computing, if you want. But think about this as you like. You just do a product state Hamiltonian. You do 1 time step of a commuting Hamiltonian, and there's no conditioning, no quantum gates, no nothing, but you just measure all qubits in the X spaces. You take a photo, and that's what you do. So again, single-site addressing is possible within limits in cold atoms. That's maybe the hardest bit in all this, but you're not conditioning anything, but you're just sampling out. You take the raw data of what you get. So a product state, 1 unit of time of a commuting Hamiltonian, and you measure out everything. It doesn't get any simpler. I mean, it's really, almost by definition, the simplest thing you can have. So product state, 1 unit of time, or 1 layer of a commuting gate set, and measuring things out. Note that every observer can be efficiently computed. I mean, just conjugate it, and you construct the tensor network. You can easily get any moment of any correlation function in polytime on any MATLAB. That's easy, but you are sampling out from this. But it's borderline classical. I mean, it's really an idiotically simple scheme. That's what it is. But the claim is it's still interesting. It's still it's a quantum supremacy scheme. There is a theorem of the hardness of classical sampling, assuming 3 highly plausible conjectures that are true on classical computers. That are true. That a classical computer cannot efficiently sample from the output distribution up to a constant error in the L1 distance. So in the same way as before, it's a quantum advantage scheme that you cannot do on classical computers, but can do on this thing. But a product state, 1 unit of time of evolution, and you sample things out. That's what it is. I say, how is this possible? I mean, it's like basically almost a classical scheme. How can there be a quantum advantage scheme happening? That seems weird. So what's going on here? Okay, so I don't have the time to go into details. I will not do it, but I will say a few words still, and then we kind of meditate a bit more about it. So the thing is, it's a 2D setting. There's no conditioning, no gates, no circuits, no nothing. But what is true is that this quench architecture can be related to a post-selected measurement-based quantum computing scheme. Yeah, so there's no quantum computing, but in fact, one can see that the output is as if one had done a measurement-based quantum computing scheme with measurements in the XY plane. So the statistics you get is the same as this scheme. Even more interesting is the insight that, in fact, the output at the last row that you have of this scheme is, well, as one says, universal for post-BQP. In fact, this is like the output of a random quantum circuit involving T gates, Z gates, control Z gates, and Hadamard gates. You're not implementing this circuit in the lab. There's no circuits. There's no gates anyway. But the outcome, the statistics that you get is as if you had done this circuit. It's like a space-time diagram, if you want. I mean, you just measure. No conditioning, but the measurement itself is as if you read this guy as a space-time diagram, and the output at the top level is as if you had done the quantum circuit, but you're not doing it. But mathematically, it's the same thing. That's interesting. So it's a mathematical equivalence of statistics that you get, and that is a post-BQP setting. So it's like a post-selected universal quantum computer. Now, this is already good enough. It's known that this gives rise to a statement that it's sharply hard to approximate the outcome distribution, which is good, and that already implies that you cannot sample from the output distribution up to a very small error in the total variation distance, to an exponentially small error. That's great, but it's it's not very practical. It's too small an error, and that's hard to achieve experimentally. So one would have to work a bit harder, and that's where these other properties come in. One assumes that the polynomial hierarchy is not collapsed. That's kind of a variant of P is not being NP. I mean, if P was NP, there would be a collapse of the polynomial hierarchy to the lowest level. It's basically a refinement of that property. One would commonly assume anti-concentration of the distribution, like a broadness of the distribution that you have in some way, and average case complexity in that the average case instance is just as hard as the worst case instance. And then one can work hard to make use of the so-called Stockmeyer machinery that takes as an input the sampling algorithm and the X, that's the outcome of that sampling, and spits out up to a multiplicative error the probability of getting that specific outcome in the computation. And putting that together, one would find that, as stated, up to a constant error in the total variation distance, you cannot classically efficiently sample from the machine. So you go into the lab, you have a square lattice, there's a product state, you switch on the interaction. It's 1 unit of time step, 1 unit of time, and then you measure, and that's all you do and have, and what you get out is a distribution that you cannot sample from in classical efficient terms. So again, assuming 3 highly plausible conjectures, a classical computer cannot efficiently sample from the output distribution of our scheme up to a constant error in the L1 distance. So this is a quantum advantage scheme, but one where you just prepare a state, you let it go for 1 unit of time, or equivalently run a 1 unit depth circuit, and then you sample out, and that's all you do. And that's a quantum advantage scheme. It doesn't get any simpler. I'm pretty convinced to be true. As a side remark, we can bring this down. In fact, we worked very hard to prove, and when we joined forces with friends at Berkeley and also in Maryland, now Chicago, of proving anti-concentration, where we worked hard to actually show that the output probability of a family of unitaries as we have it does anti-concentrate here. And that's a very nice way of proving this, we do this via the proof of this of the respective circuits giving rise to certain unitary designs, which is done by relating the problem to lower bounding the gap of a condensed matter Hamiltonian. That's actually a quite neat proof technique where you go from a lower bound of a condensed matter Hamiltonian to the convergence of a random circuit to a design to then find that the output probability has the anti-concentration property in the right fashion. And that's the anti-concentration, and the average case hardness is that's true for exact sampling. Okay, fine. But again, we could show that it's not only hard in worst case complexity, but average case hard. It's very difficult to find average case hardness results. It's one of the few examples where this can really be stated. So this loophole, if you want, can also be closed. It's also, you don't have to assume this. I mean, at least in the sense of exact sampling. So there's near-term quantum devices that are intractable on classical computers. That's kind of this milestone of quantum supremacy, of quantum advantages. And here, what I've showed you is a very simple scheme. You prepare a product, you do one unit time step, and then you sample out at the end of the day. But there's one last thing I say before I move on to our meditation part, which is there's a nice, neat property of this scheme that's hard to get otherwise, or comparably hard to get, which is it's verifiable in a very strict sense. I mean, you can, with the order of n many measurements, detect the closeness in the right sense. In fact, the heart of the matter is that what you do is a ground state of a fictitious frustration-free Hamiltonian. You can take data in the lab of a very similar type of the ones that you've anyway taken. It's not just X measurements, but X and Z measurements. But there's no conditioning, no nothing. You just take raw data of the same type. And then using these data, you would compute certain properties, and you would estimate the noise levels that you get. And if the noise levels are too high, we say, oh dear, great experiment, my friend, you've done a beautiful job, but you know what? It's the right thing, but your experiment is too noisy. There's no quantum advantage. It's that's not going to happen. It is what it is. It's still interesting, but it's not going to work. But if the noise levels are low enough, you're not getting just some justification that it's a good thing, or some qualification that you've done the right thing, or that you can build trust in the correctness of the device, or something like that. But you take data, and the estimates that you get do provide a bound of the closeness in the L1 distance, so it's providing precisely the right qualifier that you also need for the complexity theoretic proof. So when the green light goes on, you're not building trust in the correctness of the device, or think that, oh, it's kind of nice, it's kind of good. No, you're really estimating the very same property that you need in the complexity theoretic argument. And that's quite powerful. So you can with efficiently and very simply, just by local measurements, approve the device and see it is doing the right thing. And they say, oh, that's great. What's the output? I mean, what's the output? Can I now sample from the distribution? No, you can just say it's correct. And they say, what is it? I don't know. You have to build the device. You have to go to the lab. You have to do it, because you can just in this way check the correctness of the device, but you cannot efficiently make predictions of the outcome. So it's an interesting state of affairs that you can check the correctness of something that you cannot make efficient predictions about. This is interesting. So this is a scheme that's with very simple local measurements, also efficiently verifiable. That's just due to the fact that it's just a simple scheme that has a product state, one unit time evolution, or a nearest neighbor gate, and a product measurement. So we are back to the common prejudice. In order to be able to verify a quantum device, you need to be able to efficiently simulate it. It makes perfect sense. It's reasonable to assume. It's a commonly stated statement, and that's great and wonderful. Fortunately, it's not quite right. And there are some delicate settings where one can verify the quantum device, even though you cannot simulate it. So there's some trustworthy quantum devices that can be verified even if the classical simulation is beyond reach. You have to go into the lab, you have to do it, but once you get the data, you can just check whether it's right, whether it's correct in a very strong sense. It's not device independent, so the measurements don't have to be perfect and so on, but they should be quite good, because I mean, the result of earlier still states, but with quantum measurements, you can efficiently and meaningfully check the correctness of the machine, even if the classical simulation of the same machine is not within reach. That's an interesting state of affairs, and that challenges previous prejudice. There is simple quantum advantages of having a product state, 1 unit of time, and you sample things out. We've just joined forces with both with Innsbruck and with friends in Garching, with our called atomic friends, who think of realizing this in large-scale optical lattice experiments, which is kind of an interesting state of affairs. Good. So that brings me to the end of my presentation. Analog quantum simulators already outperform good classical algorithms. We've seen this at the beginning of the second lecture. We started from what quantum computers are, what they can do, what complexity classes, what variational quantum algorithms are, and have seen that simulators are already outperforming good classical algorithms in that sense that they would provide insights into problems, into physically meaningful settings in an accessible way, whereas classical computers cannot keep track of the same setting in polynomial aka meaningful time. In the sense, already existing quantum machines are outperforming classical computers in a meaningful fashion. So there is hope for feasible quantum devices to provide a super polynomial speedup of some kind, where the claim is rooted in the language of computational complexity. This is what a quantum advantage scheme is about, where you want to be precise about in what way you get a speed up in the language of theoretical computer science that's beyond the lack of imagination of the respective algorithm. Now, these schemes are not fault tolerant. They're not even error corrected, but they can be certified like a Bell test for quantum computing. And that's interesting that you can certify the correctness even if the simulators exhibit a computational speedup. You can say, I have done it. I have achieved a speedup or a quantum supremacy scheme, but you cannot just do everything classically efficiently. You have to do the scheme. You have to do something, but there are some delicate settings where you can even check the correctness in a simple fashion using quantum measurements. Again, not in a device-independent fashion, but you check the correctness even though you cannot make predictions of, you cannot make classical algorithms sample from the same distribution. That's nice. And so it makes perfect sense to think of Bell tests for quantum computing in this very strict sense. And what I've hinted at on the gaps and blah, 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 this kind of closes the conceptual loopholes of achieving such gaps that live up to very demanding prescriptions. That's wonderful. And it's a good baby step. It's a good start. And for good reason, these things are creating a lot of interest. Of course, that's only a first step. We want to move on. It's good to do this properly and to close the conceptual loopholes, but it's also good to move these schemes to physically more interesting schemes. And what I've said on the simulators, on the many-body readings, already a good push in that direction. But it would be nice to relate this more to like a proper disordered setting. In fact, what I've said is already in some way a disordered many-body Hamiltonian setting, if you want. But then if you ask Juan Jose, he would say, yeah, great, you're right. But it's still a bit computer sciencey in flavor. So can you move this closer to physicsally interesting settings while retaining with the same rigor these strong statements about quantum advantages? That's really what we want. We want more physically interesting schemes while retaining that rigorous mindset of making statements about the type of quantum advantages that we can hope to see. Equally interesting, or even more interesting if you want, would be to relate this more to structural problems. So problems of optimization of the type I mentioned earlier, and also that Jacob mentioned even earlier before my lecture, on doing QARA, on doing optimization. So what can be said in rigorous terms about this? So can we also think of practical quantum advantages of a kind, and not of the physicsy type? Because if we talk to physicists, they are just already happy about this. They say, yeah, great, we do our simulations, and then whenever we are better than what our friends can do, then we've done something cool. And I mean, I'm not there to judge this. It's meaningful, but if you think of quawa, recursive quawa, or any variant of that type, it would be good to have some handle on structure problems that are interesting for end user cases. When your friends at Airbus call you and they want to have their problems settled on a quantum computer, you want to have some rigorous understanding of what's going on and how this relates to a quantum advantage of some sort. It's very common and very fashionable to throw all kinds of data on a quantum computer and hope for the best. That's interesting, but it's not very interesting, I would say, in the sense that we have to work harder to give more substance to this and understand in a more reliable, more mathematically sound flavor what's at stake. At least that's my perspective on the field, and what we can hope for and what regimes we can really hope to get some kind of scaling advantage of the kind, or where not. That's also interesting to dequantize settings and find regimes that look quantum, but are not quite because you found an intricate classical simulation algorithm. Like, I mean, one example of that kind, we have one paper in the making that looks at MBL Hamiltonians and long-range Ising models with a transverse field that look quantum. They also built a lot of entanglement up in time, so the plain vanilla tensor network algorithms don't do the job. But then we say, haha, we have found an algorithm that does it in an efficient fashion. You say, how is this possible? That's too much entanglement. It's not going to work. Yes, but we have an algorithm using a different technique. That's also interesting because it tells you where the line is between quantum and classical, but you want to have an insight onto more structured problems also in the optimization realm. I, again, gratefully refer to Jacob Monte's talk earlier where he tackled these questions or made you interested in that type of questions. That's where you want to go, and you want to be more sound about this, more rigorous, have a deeper insight what's in store. And again, we have to deliver because otherwise the field might be in trouble. Then robustness of quantum devices. What happens under noise if you don't have error correction? It's not obvious. Is there a scope for quantum advantages without error correction? Or where is it? Or classical error correction? Readout. How can you read out quantum simulators? It's not obvious again. This is a paper I think I show that's from last year that's on a readout in cold atoms, which is kind of cute as a quantum readout scheme where we did, well, that's a long story. It's a quantum field setting where we did a retrodiction in a compressed sensing mindset. Ask me about this if you're interested. It's quite interesting. But where you look at the setting where you can only measure one quadrature in a situation where the system looks completely dead, but from taking time slices, you can still get coherent information to quantum readout, and then you can say there will be a recurrence coming later. Please be prepared. And then the system runs on, and then whoops, precisely at the anticipated point, there is the recurrence coming. That's interesting. Why am I saying this? Well, because that's sometimes overlooked. The readout of quantum devices is sometimes quite delicate and interesting and not easy, and we have to work harder on this. And maybe the last point I want to do before I thank you for your attention is that it's also conceptually interesting to think of these quantum advantage schemes, and also because it tells insightful things about how quantum circuits and quantum devices can be massaged in space and time. We know that there's space-time trade-offs, that you have a quantum algorithm and you can make them a bit broader at this while being a bit shorter, or you can make them a bit longer while using fewer devices. People talk about the quantum volume and so on as a figure of merit of how good quantum computers are. Never mind, there's some flexibility of doing that. That said, the scheme I've just advertised to you of having a product state, 1 unit of time of a circuit, and then you measure, is the extreme form of that. I mean, it's not a quantum circuit that's not deep. It's a unit time circuit. It's like one layer. You have a system, you have one layer of a quantum circuit, and you measure, and that has a quantum advantage. So there's this space-times trade-off, but it's quite interesting to see that you can, in this trade-off of space and time, you can all the way to the regime of having basically no time, but only space. It's 1 unit of time, one time step, or one depth of a circuit that you do, and you still can no longer keep track of that on a classical computer. That's quite inspiring, and that also allows for these efficient verification techniques. It's a nice baby step, but it's just as an invitation for the really interesting stuff that's about to come. And with this, I thank you very much for your attention, and we still have 11 minutes for questions. I'm looking forward to the questions you might possibly have. Thank you very much for your attention.
Thank you, Jens. This is very interesting, as always. Is there any question? I wonder whether students need to meditate a little bit, like Jens suggested, but do you have any? Yes, Ekaterini?
Yes, hello. So I have a couple of questions actually, but so one of the question is, so you throughout your talk you discussed a bit about the complexity classes, and then you said about this BQP class. So because I'm always like having trouble understanding this, like when I read, I always get confused about this class. So maybe it's kind of an opportunity to understand a bit better. So, for example, like quantum circuits, they're able to solve problems that only belong to these BQP classes, or can we? I don't know. Is there any chance that, for example, with NISQ quantum devices, can we can one tackle problems that belong to NP class, or no, I don't know if I'm.
Well,
what do you think? What is the case?
Okay. There's something to be said about this. First of all, I mean, there's no point in trying to find quantum algorithms that go outside BQP, because that's basically just the definition of. It's a fanciful way of saying what a quantum computer can do. I mean, just if you ask a computer scientist, hey, what is it that a quantum computer can do? They will say, oh, it's BQP. Yeah, and in this sense, that's all there is, but that's not a disadvantage, because that's a definition of the complexity class. That said, you talk about NP. Yeah, sure. I mean, there's hope to have problems that are in NP that are also in BQP, so that can be tackled in polynomial time on a quantum computer, like factoring. The problem in machine learning I mentioned, that's using a discrete log setting. These are problems that can be tackled on large-scale quantum computers, but not on classical computers, and that's great. Now, NP-complete problems are presumably not polytime solvable on a quantum computer. In fact, one of the first conferences I was ever at was one of the early QRP meetings when Ed Farey gave a wonderful talk on adiabatic computing, where he just found it was absolutely wonderful. But he thought that he had found a polytime algorithm to solve NP-complete problems. And he was like almost under drugs. Like, he was really excited about this. But in the meantime, nobody is thinking that it's possible. But what your question is a deeper one. You ask what's in store for near-term computers. And that's even less. I mean, one cannot hope near-term devices to solve every problem in BQP. We wish, but no, it's not going to happen. So the question is, what can it do? And it's not even obvious that there is a complexity class thereof, because the way asymptotics is built in languages, when you talk about complexity classes, is not very natural when you speak of devices that are noisy and finite. I mean, what does it mean to have a scalable device when the noise is also scaling up? So part of the homework, and I see this as an invitation to you, is how to make a meaningful concept of what near-term devices can do in some appropriate language, which could be the language of computational complexity, but not necessarily. So that's basically our hidden program. I mean, maybe between the lines, you've seen my meta message, my secret agenda, although it's no longer secret because I freely admit it. But the previously secret agenda was to say something rigorous about dirty and existing stuff. Yeah, while not necessarily in the language of computational complexity, but proving stuff about stuff. And that's very worthwhile, I think. But you are right. I mean, your question is spot on. I mean, what you say is the number one question of the field, which is, what can near-term quantum computers do? And I wish I had a better answer.
Thanks a lot.
I have another question. I mean, about the random circuits, I was wondering if, I mean, I don't know if they implemented the random circuits to just prove that there is a quantum advantage, or there is a like real application of the random circuits. For example, I don't know, encode information that a classical computer can uncode. I don't know if it makes sense or not, but I would like to know a bit more about this topic.
Yeah, I mean, as is, I mean, the published results is on just showing that you can do something beyond classical means. So there was no application whatsoever. But of course, people are thinking about applications thereof, and that depends on the level of forgivingness that you give to these settings. I mean, there are some algorithms where these like variants of these sampling algorithms would provide a speed up over classic algorithms that have access to classical randomness, uniform randomness. So then having access to the structured randomness can help in some optimization problems. But then you say, but over it's an advantage over uniform classical randomness. Is that really what you want? And I say, well, you have to start somewhere. So my vague answer is it's spot on once again. I mean, you two are asking the two big questions of the field. That's the good news. The bad news is you're not alone. Yeah. But of course, the question is, what can you do with this? And there's some settings. You hinted at this. I mean, of course, you can encode some problems. Of course, you can also say, are the states you generate interesting in some way? And there are. I mean, they have metrological applications. They have blah, blah. I mean, there's some things you can think about this. But when you say, oh, I want to have a random circuit that solves my battery duration problem, to then go to Elon Musk and settle his electric car problem, go for it. That's not yet there for random quantum circuits. Although I would love to. I mean, we all have our thoughts about this, but that's not quite in store yet. And that's also not published for that matter. I mean, the paper as is just says we can do it. And that's already great. I mean, with all respect. Is this a fair answer to your question?
Yeah, I mean, more than enough.
I can only say what I know.
Okay, any other questions?
So
I have one more question. Yes.
No, go ahead, Katerina.
Yeah.
So you also quickly mentioned about the quantum-assisted machine learning and parameterize the circuits for classical data. So I was wondering if one was trying to look for quantum advantage in this type of settings, like where should it start, or like which advantage would you focus? Would it be like speed up, or I don't know, memory or energy, or?
Oh, that's a wonderful question. I mean, again, the bad news is all these questions are very much spot on, and the answer is always the same. I wish. Yeah. I mean, these are, of course, the questions I really work on, or we work on. Like when you say, I mean, the paper I quickly mentioned, that's already out. I mean, that provides a proven speed up of quantum over classical device in machine learning. That's great. We've already published this. It's an exponential separation in a meaningful setting, namely this PAC learning, PAC distribution learning. Now, the good news is many problems in machine learning are basically of the type that you want to learn at probability distribution. That's just fair. Also, PAC learning may be a bit unorthodox from a machine learning perspective, but it's very, very clean and very nice. It's really that you say that with high probability, you're creating a new generator that spits out samples that are basically indistinguishable from the former ones. That makes perfect sense. And we have a proven speed up, exponential one, in computational complexity, not in sample complexity. But then you can also ask other questions on sample complexities and so on. The paper I mentioned on generalization that also asks about future performance of quantum circuits on unseen data. But all these settings you seem to hint at, namely, what oracle access do you allow for? I mean, do you have quantum data or classical data? Do you have a computational speed up or a sample complexity speed up? These make all sense. So what we know is what we know. But this is still a bit of a funny, complex concept class, because we have a tailored concept class that's tailored to make these discrete logs work at the machinery. Also, this nice work by Temme and others at IBM, this kernel stuff, is also rooted in a quantum algorithm, if you want. That's of a non-learning type. So I think what we need to learn more about what sample complexity advantages you can have. That would be wonderful. Then you want to have more practical problems of the kind. And if you have a proven separation, we want to move away, or see whether you can move away from settings where you have a non-learning type quantum algorithm running in the machinery in the background. Yeah. Now I'm saying basically all I know about this, which is not so much, but at least we have some baby steps in a good direction. But what you say is spot on. I think preferably would have a sampling complexity advantage in a setting where you don't just translate a hidden subgroup problem type thingy into a learning task. Although we have to start somewhere, and that's what we are doing.
I see. Thank you. Thanks a lot.
Okay, Juanjo, you wanted to ask something?
Yeah, well, it was a technical question regarding this last problem you showed about the two-dimensional circuit with one layer of evolution only. This kind of sampling problems, how do they behave under noise? So are they still very sensitive to noise, or are there some probable advantages with respect to other paradigms like AQP and things like that?
Oh, that's good that you say that. I mean, as is, it's robust to noise. I mean, you can do it up to a constant error in the total variation distance. So that's what you can grant for, right? I mean, you do the perfect sampling, great. And then you can add noise so that you're still within the constant one norm ball, and then you're still in business. So yes, you can allow for errors. That said, a constant error is not so forgiving. I mean, if you have like IID noise, then having a constant error means that your little thingy individually has to go like 1 over n. If you have n systems, and it's additive, like crudely speaking. Each gives some error, and then you have an order n error, which you mustn't have. You want to have a constant error so that if you scale up systems, they have to be better and better in per side. So yes, you can tolerate errors. It's all about finite systems anyway, so it's not about asymptotic. So yes, you can. But you want to work harder to be better than this n scaling. And that's research. I mean, that's interesting.
Thank you.
So again, I mean, I think now with these questions, we've gone through the big questions of the field.
And maybe a follow-up question. Yes, okay. So earlier in the previous talk with Jacobo, so we discussed a bit at the end about, I don't know if you were already in the call, about small circuits and the role of entanglement, and because now a lot of work seems to try to make like complicated circuit structures and try to, I don't know, do different stuff with this. So yeah, I was wondering what do you already know about small circuits and the role of entanglement, and generally comments on this?
That's a long question. I mean, well, small circuits are interesting because we have them. I'm not sure whether the previous speaker is still in the call. I think he is.
I think left. He's here. Yes.
I
mean, his name is here. I don't know if he's.
Okay. No, it's interesting. We should think about these things. Then the role of entanglement, that's tricky because these are not asymptotic statements, right? I mean, these are small-scale devices. I mean, asymptotic, you can say a lot. I mean, I hinted at this, that you need entanglement. If you don't have entanglement, you're dead. If you have too much entanglement, you're also dead. Like one of the papers we wrote is like too entangled to be useful, which was a bit of a joke title, but it has a meaningful result in it, because if you're too entangled, then there's no way you can hope for a quantum speed up. So you have to strike the right balance somehow. It has to be diluted in the right way. But these are asymptotic statements. So for a real device, well, I mean, if you're If you're not entangled enough, then presumably you cannot hope for a quantum speed up. But how that precisely is working, it's not so clear. Again, that's an invitation to you, I would say.
And then a quick follow-up question, sorry. So you already said about the importance of entanglement for quantum advantage. So, I mean, so far as I understand, so there are two main things that actually are the mechanics of quantum advantage in all of these quantum simulations and quantum computation is entanglement and superposition, right? These two basic things, or am I missing something?
No, I mean, of course, at the end of the day, that's all you have. I mean, you have to exploit entanglement. Well, entanglement is just another way of a non-local superposition, so that's what you have to exploit. And I mean, the insight about this is that, I mean, early on, people thought about entanglement as if it was like a currency. You go to the shop and then you buy a car by putting money onto the counter, and people thought that, oh, you need entanglement and more is better and great, and then you can transform one way to the other and so on. And over the years, we have learned that this is kind of true and kind of not true, in the sense that the specific structure matters, and to just say I have entanglement, then it's quantum, means nothing. I mean, there was in a way also the well, I don't want to like say anything bad about anybody, but like one of the challenges of the early discussions on annealers and D-wave was that they had very loud claims, and people thought, oh, is it quantum? And then they got very nervous, saying, oh, I don't know, but we have a device, which is great, by the way. But then people said, oh, but it's classical. And then they sat down and computed entanglement witnesses, said, oh, but it's coherent. And say, yeah, that's great, but I don't know. I mean, that doesn't mean anything, because you need entanglement in a certain flavor and the right structure and so on. And that's not so obvious when you want to have a computational advantage. So lesson, yes, you need entanglement, but it's delicate. Just to have entanglement alone means, unfortunately, nothing. It's just more difficult than this, I fear.
Mm-hmm. I see. Thanks a lot.
That's my honest answer.
Okay, Jens, thank you for the answers and for the nice talk.
Wonderful. Yeah, I'm already 6 minutes late for a Zoom call on something on quantum machine learning. Thanks for the interest, and enjoy the rest of the day. And there's a bit of school still tomorrow, right?
Yes.
Yes, there is a talk by Roberta Zambrini on quantum machine learning, reservoir computing, which is
wonderful. Oh, good. Then
if you are curious, you can join us.
Yeah, good. Thank you. Have a good day.
Okay. Thank you, Jens.
Bye-bye.
Thank you.
Thank you.
Bye-bye.
I would like to